Hi there, we're back for a video which will seem a little bit out of left field. We've been talking a lot about derivatives, and now we're going to kind of switch gears and talk about a different topic that's important in calculus, and that's the topic of area and how things accumulate. So in this video, we're going to talk about what an integral is, give you the basic idea of it, and then later on in the course, we're going to talk about how the idea of a derivative and an area relate to each other. So here we go. So we're going to do an introduction, and then we got a couple of examples that we'll work through, and then our summary. So the idea is like, well, how do we find area? So you have to kind of go back into our brains and think about way back when you first started learning about area. Well, it's actually really kind of an ancient problem. So the idea is, can we find the area of any shape that's defined by a particular function? All right, including something like the area of a circle. Now, you probably have known for a long time the area of a circle area is pi r squared, but we didn't know that for forever. And where's pi coming from? What's the deal with all this? Well, back in the days, the ancient Greeks used this method called the method of exhaustion. Not because they're exhausted, but because they're continuing to estimate the area of a circle by inscribing it with some sort of a shape, like a pentagon or a hexagon, or shapes that have more and more sides. And the idea is that as you increase the number of sides, you should be able to get closer and closer to the true area. And if you can find the area of this particular shape that we've got, we can use it to approximate the area of the circle. Okay, so this is kind of the idea of what's going on here. Our idea is not going to use like a pentagon or anything like that, but we're going to use a simpler shape called a rectangle to find and approximate the area between a function and the axis. And the idea is that the more rectangles we use, the more accurate our approximation is going to be. So let's introduce you to a little bit of terminology. This right here is what we call a definite integral. So we say that call it the integral from a to b of f of x dx. And what it's going to find for us is what we call signed area. So what I've done right here is I've drawn an example graph. And what's in red is what we're going to actually count as our area. So in this case, over to the left, we've got area between -2 and 0 for a function that is above the x-axis. And we've got the area between the x-axis and the function from 0 to 2. Notice that function goes below the x-axis. Now, normally when you first learned about area, hopefully the idea was that the area was positive. But here when we're going to integrate, if we integrate and we have area below the x-axis, we're going to count that area as negative. So that's what we call signed area. In other words, we want a sign attached to our area. There'll be some other things that we'll discover with this later, but this is the basic idea. Okay, a is what's called the lower limit of our integral. B is called the upper limit. And then f of x is what's called the integrand. All right, and so in all of this, what we're going to do is we're going to try to find the area underneath this curve by counting area that falls below the x-axis as negative. And just it'll be a little bit different in a couple of days, but stick with that idea for now. Here we go. I've got this example function right here where all we've got for this function are outputs. All right. The output at 0, for example, is 7. Output at 2 is 1. And then we got all of our outputs all the way up until 15. So I drew all those points right here with the dots. And our first idea is, well, can we find the area underneath this curve? We don't know necessarily what the curve looks like, but we can use rectangles to try to get an approximation of what the curve might look like. All right. So we're going to use what's called a right rectangle approximation. And the idea is, scoot it back a second. The idea is the right side of a rectangle will meet up with the function. And the area of this rectangle will be our approximation for the area of underneath the function for that little portion of time. So for example, it's easy to see right here between 2 and 3, I made the function 4 units high. Well, that's because the right endpoint of our rectangle at 3 is 4 units high. When I went and made the rectangle from 3 to 5, right, that height was -2. So I drew a little rectangle that went down to -2 because -2 was the height at the right endpoint. When I went to 5 to 8, what do you think is going to be the height of this rectangle? It's 8, because that's the height of the right endpoint. So I went through and I created all of these rectangles, all right? And the idea is if we can find the areas of each of these rectangles, we'll be able to find the area under the curve, at least an approximation for it. So that's what we're doing right here. We're going to find the signed area, the integral from 0 to 15 of f of x dx. So let's write this out. What are we actually doing? Well, we're approximating for one. And we're saying, well, the width of the first rectangle is 2 minus 0. And the height of that first rectangle is the height of the right endpoint, which would be at f of 2. And then we've got the rectangle from 2 to 3, so that width is 3 minus 2, times the height of that rectangle at the endpoint 3. So we put f of 3 there. And we keep on going. We've got 5 minus 3 times f of 5. 8 minus 5, the width of this rectangle, times f of 8. We've got 11 minus 8, which is the width of this rectangle, times f of 11. And then 15 minus 11 times f of 15. And of course, we know what these values are. They gave these values to us in the chart. So I plug in f of 2 is 1, f of 3 is 4, and so on. And so we get an estimate for this area to be 41 units squared. And we don't have units in this case, so there's no need to worry about it here. What happens if we did a left rectangle approximation? What would be going on here? Well, it's the same process. We still have a rectangle that's going to go from 0 to 2, and 2 to 3, and 3 to 5, based on our intervals here. But in this case, the rectangle is as high as the left endpoint. So for example, the very first one that I'll write will be the rectangle from 0 to 2 with a height of f of 0. So you see how I wrote that here? Width is 2, height is f of 0. The next little tiny rectangle here has a width of 1 and a height of f of 2. And then we've got a width of 2 from 3 to 5 with a height of f of 3. And so on. So it's the same process as before. We're just using the left endpoint of our interval to form our rectangle. Notice how I left out my lonely right endpoint there, because it's never the left endpoint of a rectangle. Okay. So again, I go to my chart. I plug in 7 for f of 0. 1 for f of 2, and so on, and plug in all these values, and so I get 13. Not quite the same approximation as before. I'm not saying this is completely accurate, all right, but the idea is this big rectangle right here gives us a lot of negative signed area, whereas before, when we did it, we had a big rectangle right here with positive signed area. So that made a huge difference. Okay, so that's our approximation with a left rectangle approximation. All right, so an example for you, use a right rectangle, left rectangle, and what we call midpoint rectangle approximation with 5 rectangles to approximate the integral from 0 to pi over 2 of cosine of x dx. So here's the graph of cosine of x, and I've got all of my endpoints listed right here. All right, so if we're going to use a right rectangle approximation, what I'm going to want to use is the rectangles that are formed when I divide my interval into 5 subintervals. So I've got pi over 2, and I want to divide that up into 5 subintervals here. So pi over 2 divided by 5 would give us pi over 10 as the width of each of our rectangles. So we would say pi over 10 is our first rectangle width. And then we've got a rectangle from pi over 10 to 2 pi over 10, or pi over 5, 2 pi over 10 to 3 pi over 10, 3 pi over 10 to 4 pi over 10, and then on to pi over 2. So our rectangle approximation will look a little something like this. The rectangle from 0 to pi over 10 with the height of the right endpoint, which is at pi over 10, so that's 0.951. And then I've got another rectangle from pi over 5 to pi over 10. That height is going to be 0.809. That's cosine of pi over 5. Then I'm going to use 3 pi over 10 and 2 pi over 5, and then pi over 2, all of my right endpoints of each of these intervals when I divided up evenly into 5 subintervals. I plug in my numbers from my chart. I went ahead and actually calculated all these for us, and I get 0.834. If I'm using a left rectangle approximation, it's the same idea, except I'm going to start on the left. So notice my very first rectangle still has a width of pi over 10. That's a fifth of pi over 2. but it's going to start at cosine of 0 instead. And then I form a rectangle from cosine of pi over 10 to pi over 5 with the height at pi over 10. That's this. Then we got pi over 5, 3 pi over 10, and 2 pi over 5. Notice I'm leaving out pi over 2 because that's the farthest right endpoint. Again, I plug in my numbers, and I get 1.149. So the left rectangle approximation gave us a little bit higher of an approximation. All right, finally, we've got what we call a midpoint rectangle approximation. So remember how I said that I was going to divide up my interval into 5 regions? Okay, so instead, I've got my rectangle that goes all the way over to pi over 10, one that goes to pi over 5, 3 pi over 10, and so on. Okay, so just ignore the heights. I'm just trying to show you what my regions are. The midpoint approximation is going to actually give us the height of the rectangle at the middle x value in each of the intervals, right? So in this case, the middle x value is actually pi over 20 in the interval from 0 to pi over 10. The middle value in between pi over 10 and pi over 5 is 3 pi over 20. Then we have 5 pi over 20, that's halfway in between these two, 7 pi over 20, and 9 pi over 20. So when I say the midpoint approximation, we're using the middle x value to form the height of our rectangles. And so we go to our chart just like before at pi over 20, 3 pi over 20, 5 pi over 20, 7 pi over 20, and 9 pi over 20. And we plug in our values from our chart and get 1.004. All right, one last thing that we could do is we could use trapezoids. Now, if you view this diagram right here, you notice that a trapezoid actually fits it well because it's like a mix between a triangle and a rectangle. So if you remember, our formula for the area of a trapezoid was average our heights and multiply by our base. So you probably learned this as base 1 plus base 2 divided by 2 times the height. Well, this one's a little bit different because we're actually going to be orienting our trapezoid going up like this. Okay, so I like to think of it as averaging our two heights, in this case 4 and 9, find the average of those two, and multiply by our base. For example, I've got another little chart here, and we want to approximate the integral from 0 to 6 of f of x dx using 6 trapezoids in the following data. So to set it up, what we're going to say is that we're going to average the first height, f of 0 and f of 1, and multiply by a width of 1. So in this case, the trapezoid would have a height of 12 and a height of 10, and we're averaging the two of those, and then multiplying by a width of 1. The second trapezoid will have a height at f of 1 and a height at f of 2, and we average those two and multiply by 1 again. So notice I'm just taking the heights at each of the endpoints and averaging the two of them. Later on in class, we'll see how that's connected to something else that we've been doing. And I'm going to plug in my values. This is kind of the boring part, but I plugged in 12 for f of 0, 10 for f of 1, and average the two, multiply by 1, and we end up with 74. Of course, all of this can be applied using to real-life situations. So for example, if I had a situation where I was given velocity of an aircraft that's traveling due west, and the velocities recorded were during the first 10 minutes, can I use trapezoid to estimate the distance traveled? Right, so that's this area under a positive velocity curve. More on that in class. But here the idea is we can approximate our distance by finding trapezoids. So we say the average of V1 and V0, right, would be our first trapezoid times a width of 1. Our second trapezoid goes from 1 to 3, so we average those two and multiply by a width of 2, and we continue on to do that. And then when we plug in our values, all right, there's a lot of computation that goes on here. We end up with 12.75 miles. So the idea is when we integrated, the term we're going to use here, the velocity curve, we took away the per part that was the derivative part, and we got back to our original distance, which was in miles. So that's going to be a general theme for integrating and finding units. In summary, we've been introduced to the concept of the definite integral and our notation for finding signed area between a curve and the x-axis, and a variety of shapes from rectangles to trapezoids can be used to estimate this signed area. I know this was a little bit longer, but a lot of good information. We'll talk about it again in class. Thanks for being patient. We'll see you then.